Hello everyone, welcome to lecture 25. You see, today what we will do is we will review the internal forces in plane frame. Okay. Now see some examples of frame. These are some example of frame. Okay. No, not example of frame, it is some structure. Okay, I mean we have not seen, we don't know whether they are frame or different other structural idealization, but these are some structure. This is a bridge, as a Howrah Bridge. This is Eiffel Tower. This is a building. The assembly of beams, columns in a building. This is a cycle frame. This is a chair, the folding chair. And this is also a loading frame. This is very common in if you go to any gym. This is multi gym. This is human skeleton, and again this is a drafter that you have used in your engineering drawing. There could be many other examples, such examples. Now these are some. Now in the first class I showed you some examples of structure. So here the purpose is not to purpose of showing all these figures is not to tell you what structure is. The purpose is different. The purpose is, you see, can we find out some similarity between all these structures that are shown here, and the similarity, if you look at them very carefully, so what are the common thing on all this structure? The common thing is, if you look at them, they are all, it is a structural system which consists of skeletal members. Now, for instance, if you see this structure, this is a collection of all these members, skeletal members. This structure is also collection of all these members. This structure is also collection of this and this frame. This human skeleton is also collection of these ribs, then these bones. This is also a collection of these rods, and then this angle. This is also collection of these. You see these rods. The cycle is also collection of this length, this rod, and this. All are individually slender members. So the common thing between all these structures are they are essentially a collection of several skeletal members. Now, how these members are connected, how these skeletal members are connected, depending on that we have different structural idealization, right. So if you remember, when we introduced truss, we said that truss is also a collection of skeletal members, slender members, but in that case, in truss, slender members are connected at the end through pins. Now so this was truss, right. We already introduced truss. These are all slender members individually. They are connected through pins at the end. And also the another important point, important part is in truss we cannot have force like this. We cannot have force on the member. If the force always has to be on the joints, right. And of course we have supports. Now consider a system, again a collection of these skeletal members, where these conditions that we had for trusses, these conditions are released. Then what we have? This is, first you release the condition where the members are, now the members are not necessarily be connected through pins. So remove these pins. Okay. Now the next restriction is also released, where now in this structure, suppose the forces can have on the members as well. Okay. Now the structure what you get, this is no longer truss, right. Though the shape remains same, but the structural requirement for an object to be truss, for a structure to be truss, is not applicable, is not valid here, is not satisfying here. Now, though this is no longer a truss, so this is a frame. Okay. Now, so let us see what are the differences. So if this is the truss and this is a frame. Now, if you look at the joints, we said that in truss all the joints are pin connected, but in frame those joints could be pin connected. Some of the joints are pin connected, some of the joints are rigid, but when in a frame all the joints become pin connected and the loading condition also satisfied this, then this become this will be converted to this can be idealized as truss. Okay. Now from the analysis point of view, what is the consequence of releasing this restriction? The major consequence is when we study structural analysis of truss, then one of the what makes our life easier is all the members in truss are two force members. Okay, so if you take a member out from the truss, only forces you have is the two forces at the two end, and that the two collinear forces at the two end, and they are equal and opposite. That makes our analysis easier. But now in frame, since those restrictions are released, the members are not necessarily be two force members. Okay, then what is the characteristic of those members? Now, so now before we do that, let us define frame. Then what is frame? Frame is a structural system that consists of skeletal members. Just now we have seen that it is an assembly of several skeletal members which are capable of resisting externally applied load by, in case of truss, by developing axial force, but in case of frame it is by developing axial force, bending moments and shear forces as well. There could be twisting moment also, but since we are talking about plane frame, these are the major three internal forces that we need to consider. Okay, but in case of truss, there was no bending moment and shear force, it was only axial force. Now, so what is the consequence of that? Suppose this is a truss and this is a frame. If we remove a member from here, or if we break a member in a truss, then the internal forces are only the member forces. Okay, because all members are two force members. Whereas in the case of frame, the situation is different. We do have this force in frame, but in addition to that, the effect of bending moment and shear force also need to be considered. So if we break a frame member and then draw the free body diagram of that, then in the free body diagram we have all the forces like beams. We have this axial force, we have shear force, and we have bending moment as well. Now there is one important point to be noted. In beam also, ideally we have bending moment, axial force and shear force, but when we analyzed beam, if you remember, we said that axial force was neglected. It was assumed there is no axial force, at least the loading condition we have considered so far. There was no axial force developed in the beam. That is why you did not consider axial force, and even if you consider, the axial forces were 0. But in case of frame, we will see that the axial force also plays a very important role, and along with bending moment and shear force diagram that we did for beam, we also need to draw axial force diagrams. Okay. Now let us give you let us make one important point. The truss is one extreme case where all joints are pin joints, but there is no compromise with that requirement, right? But in case of frame, we can have joints, we can have different kinds of joints. Some of the joints are rigid joints, means those joints do not allow any rotation. Some of the joints are pin connected. And now just to give you an example, suppose if you take a tripod of a camera, many of you might have seen this. This is a frame. Now, but if you see this joint, all these joints are pin joints. This member can rotate about this joint, this member can rotate about this joint. these 3 members also pin jointed. If these members also can rotate here, can rotate here, can rotate, there is no rotational constraint in all these joints. But still it is not a truss, it is a frame. Why it is a frame? Because one of the another important part in the case of truss is all these members are separate members. Okay, they are connected only at the end. Now here this is a continuous, this is one member, and this member is connected to this member at some intermediate point, not at the end points. Okay, so if it is, so these members cannot be treated as two force members, because the reaction from two force members is we have forces only at the two ends, and those two forces are collinear forces. But in this case, because of the reaction from this member, we can have a force on the member itself, not in addition to the ends. We have a force in member itself. So these members are not two force members. So this cannot be idealized as truss. So this is a frame. But in this case, the frames are pin jointed. But in this case, you see, this is a factory shed. This is a frame, but this frame is not pin jointed. This joint is rigid joint. So there is no rotation is allowed at this joint. So this member and this member, joint between these two members are rigid joint. If you take a frame of a cycle, this is a frame, and these joints are also rigid joints. These joints, there is no rotation allowed in these joints. These joint, all are rigid joints. Now on the other hand, this is a collapsible gate. You all have seen it. Collapsible gate is a very interesting structure. You see the name, the collapsible gate, right? The gate which can be collapsed, which we can ideally we want our structure not to collapse, right? That was the safety requirement. But it is one example where we make a structure such that if we apply load, the structure is collapsed. Okay, that's why it is called collapsible gate. Okay, now this is also a frame. This is a member. These are all different members. They are all connected through pins here, but these members is a continuous member. This is not that different members are connected at the end. So this is not a truss. So this is a frame, but in this case the joints are pin joints. Okay, so in a nutshell, that in frame the restriction for truss is released, but the joints of a frame, we can have a rigid frame where all joints are rigid joints, where the rotation is not allowed. We can have a frame which is pin jointed, which can have a we can have a frame where some of the joints are rigid and some of the joints are pins. Okay, now let me show you some example. Suppose take a frame. Okay, this is called portal frame, and which is supported at point A and supported at point D, and we have a joint B and joint C. Okay, and this is applied, this is subjected to some horizontal load. Okay, this is a problem. What we'll see next few slides is, see, in this problem we have not defined what we say the joint point A and point D is supported, but which kinds of support we have not specified. We say the joint B and joint C, they are joints, but which kinds of joints we have not specified yet. What we'll see next few slides is we'll change the different kinds, we'll see different kinds of support and different kinds of joints, and then for the same frame in same geometric shape, but the different connections between the members, and when they are applied to same horizontal loads, then how all these frames behave. So with that, probably you can have a better understanding of the effect of different joints and support. Okay, now the first case is this case is this end is the fixed end and this end is also fixed end, and this joint is rigid joint and this joint is also rigid joint. Rigid joint means now between this member and this member, if the initial angle is 90 degree, that angle is always preserved. There is no rotation allowed between this member and this member. And if you look at them, this deflected shape, you see this angle and this angle. If you draw slope at the deformed shape, slope at this member and slope at this member, you will see the angle between these two slopes remain 90 degree. Here, the same here, angle between these two slopes remain 90 degree. But whereas in this case the support condition is same, but now the joints are not rigid joints. We have an internal hinge here. Okay, so hinge means it allows rotation, it cannot give constraint against rotation. So naturally this angle between this member and this member changes, and which is evident from this animation. So if you draw the slope, then you will see these angles are not same. Okay, now in this case the angle is increases, the angle increases, and in this case angle decreases. Now in the next case, again the first one is fixed, and now in this case this joint is not rigid, it is pin joint, but other joint is rigid. Now you see these joints the angle remains 90 degree, whereas in this joint the angles does not remain 90 degree because it allows rotation, because we have a internal hinge here. Okay, now but the same now again in this problem is this fixed support is replaced by hinge support, and we have both hinge at this joint B and joint C. Now see, when it was hinge support, then when it was fixed support, see the rotation at the slope at this point is 0, but in this case the slope is not 0, and that is the characteristic of hinge support. It does not give any constraint against rotation. Okay. So you see, so the same problem in same geometry, but with different support and different joint condition, they behave differently under the same load. Okay. Now this is another example. You see, it is just it's a cantilever frame kind of thing. One end is fixed, but the other end there is no support here, and how they behave. Now these joints are rigid joints, and you see the 90 degree angle is preserved. 90 degree angle is preserved. In this case also these joints are rigid joints, but this is hinge and this is roller, and this 90 degree angle is preserved. If you draw slope between these two angles, the angle between these two slopes will be 90 degree. Here also the same thing. Okay. Now now as we have defined what is frame and how in a frame we can have different kinds of support and different kinds of joints. Again, when you look at any frame, when you see any frame, then please look at their joints, look at their support condition, and then you decide yourself whether if you look at any structure, then you decide yourself then whether the structure can be idealized as a truss or as a frame. Okay. Now this lecture is on determination of internal forces in frame, for drawing bending moment, shear force and axial force diagram for a frame. Let us just demonstrate through one example. Now this is a cantilever frame, which is one end is fixed and another one is applied load is P. We need to find out what is the bending moment, shear force and axial force diagram for this frame. Okay, this joint is rigid joint. So first is take these two parts separate, AB and BC, because we are two members. Now when we draw the bending moment diagram and shear force diagram or axial force diagram, we have to draw it for BC, we have to draw it for AB. Now let's separate them. This is BC and AB, and draw the free body diagram of both the parts separately. Now draw the free body diagram for C. This is the externally applied load P at C. Then since it is this frame, we have axial load FB, then shear force FB, and then bending moment MB. So this is the free body diagram of part BC, free body diagram of part BC. Similarly, let's draw the free body diagram of part AB. First we have support reaction AX, and then AY, and then MA. This is fixed support, so all three forces we have. Okay. Now at B also we have FB and then VB and then MB, and look at joint B. When joint B belongs to part BC, the sign we used, and the joint B belongs to part BA, the sign we use, they are opposite. So therefore this, when they are connected, the net internal forces, they balance each other, they cancel each other. So this is the free body diagram of joint AB. Now you put a star and make one comment here, is joint B we have just only two members, BC and BA. We will see a situation where at the same joint we have 3 members or 4 members, and in those cases how the free body diagram of the joints to be shown, that we will discuss. But in this case it is slightly simpler case, because at B it is connected only, it is connected only to 2 members. Now apply free body diagram, apply bound equilibrium equation, summation of fx is equal to 0, fb, this will give you fb is equal to 0, fy is equal to 0, it will give you vb is equal to p, and mb is equal to 0, this will give you mb is equal to minus pa. This is straightforward, we have done it many times. Now similarly apply equilibrium condition for this part. Again fx is equal to 0, this gives us ax plus fb is equal to 0, fb is equal to 0 we have already obtained here, so naturally ax is equal to 0, fy is equal to 0, so y direction forces are ay positive, vb in this negative downward minus, and ay is equal to p, vb is equal to p we have already obtained. Similarly mb is, take moment about b, if we take mb is equal to 0, though this force will not contribute, this force will not contribute, because this passing through b, ax is equal to 0 anyway, the contribution will be from mb and ma, and this gives us ma minus mb is equal to 0, ma is equal to mb is equal to minus pa, mb we have already obtained. So now now we have already computed the support reactions and the what are the internal forces at the joint. Let us draw the bending moment diagram. Now one way of doing calculating bending moment, one way bending moment diagram, shear force diagram or axial force diagram is essentially the graphical representation of the bending moment, shear force and axial force, right? And one way of drawing bending moment of this diagram is to take a section at at a given distance x and calculate their bending moment, shear force and axial force as a function of x, and then bending moment, shear force diagrams will be the graphical representation of those functions. Okay, this is one approach. And this is the fundamental approach, but but at least for this problem we don't need that. Just by looking at the problem and by looking at the joint condition and the internal forces of the joint, we can draw the bending moment and shear force diagram without actually doing that exercise, that taking a section representing bending moment, shear, internal forces as a function of x and then represent them graphically. We can avoid that that step here. Okay, how can we do that? So suppose these were all the forces, now sum of the forces at 0, so let us remove those forces and just keep all the forces which are non-zero. So non-zero forces are these forces. Okay, now let us first draw the actual force. Now it is very important, you see this VB was shear force for BC, but the same VB for AB it becomes axial force. Now FB, which was axial force in BC, but the same FB in AB becomes shear force, but bending moment it remains same. So because the axial because they are in opposite, their directions are different, that's why when you draw shear force and bending moment, shear force and axial force diagram, please check that. Now so this was the shear force, P was the shear force for BC, but the same P becomes axial force for AB. Okay, and anyway these the horizontal direction, all the forces at 0 anyway in this case. Let us draw the axial force diagram. So what would be the axial force for BC? There is no axial force for BC. And what is the axial force for AB? Axial force for AB is P, and which is compressive. the axial force of is compressive, this is negative sign. So, this is the axial force for the entire frame. Now, let us draw the shear force diagram. What is the shear force diagram? Now, let us first consider part BC. Now, in part BC, what happens? The shear force is shear force. Okay, shear force is positive here. Shear force is positive here, and there is no other load between BC, so shear force remain constant. And what would be the shear force? The sign, the shear force will be positive, because this is acting downward, and if we take a section here, shear force will be upward, clockwise couple will be positive, and therefore shear force is positive here. So, shear force is positive for BC. Now, let us, what is the shear force for AB? There is no shear force for AB, because the horizontal forces are 0. So, this is the shear force diagram for the entire structure. Now, let us draw the bending moment diagram. Bending moment diagram is at point C, it is tip of the cantilever. So, bending moment will be 0, and between C and B, bending moment should vary linearly. It will be hogging moment or sagging moment. It will be hogging moment, because BC will behave as a cantilever. So, between B and C, bending moment will be negative, linearly varying, and at point B, the bending moment value will be minus PA. So, BC, the bending moment is this. That is what our sign convention is. In many places, you will see that this bending moment is drawn on the other side. So, their sign convention taken different. Okay. Let us see what happens to this. In this case, again the bending moment is, and just to quick remember the sign. If you see, in our case, if a beam is like this, we assume this is our positive bending moment. This is positive bending moment, and the beam deflect like this. If the beam deflect like this, then this is compression side, this is compression side, and this is tension side. Okay. And how we draw this bending moment diagram? The bending moment diagram is drawn as this. Okay. So, this is positive. So, in this case, bending moment is positive. Now, if we take a cantilever beam subjected to tip load, so it deflects like this. So, this is tension and this is compression. And how we draw the bending moment as per our sign convention? This is okay. So, this is AB. So, this is AB and this is AB. This is AB. Okay. So, this is bending moment diagram. So, you see, in our case, always we draw the bending moment diagram on the compression side. Okay. Bottom side is the compression, bending moment diagram is drawn on the compression side. Compression side is top side, the bending moment diagram drawn is at the top side. So, but in many books and many other places, you see the sign convention is taken just opposite. The bending moment diagram is drawn on the tension side, but both are correct, but whatever sign convention you use, you be consistent with that. Okay. Now, this is our sign convention. Now, you see, okay. Now, so this is minus PA, this is minus PA. So, what would be the bending moment, what would be the compression side? Compression side will be, this side will be the compression side, because it is minus PA. So, essentially it is in this direction, the compression side will be this side, tension side will be this side. In this case, compression side is this side, tension side is this side. So, for this part, bending moment will be this, and this bending moment is constant throughout. So, this is the bending moment diagram of this frame. Okay. Now, if we see the deflected shape of this frame, deflected shape is something like this. You see, just from the deflected shape you can understand this side is compression and this side is top, this side is compression and this side is top. So, this is how bending moment and the bending moment and shear force. Okay. Now, we will stop here. Next class we will see just one or two quick example on bending moment, shear force and axial force diagram of frame. Thank you.